is equal to QL E negative T over CR. Right, you want to make Q the subject, so this will cross the equation. I'm going to get minus Q is equal to minus, let me put it this way, Q F E log CR minus, this can be minus, so it becomes Q F here. Right, good. Now let's multiply through by, or divide through by, sorry. Let's divide through by negative, or you can also say multiply through by negative. Negative 1, it's typically the same. So Q will be equal to, okay, this will become negative QF B negative T CR. This will become positive QF here. Right, so rearrange. So Q will be equal to, let's rearrange. If you rearrange, you don't get QF here minus QF here E T CR. CR is done. Right, so we are done. We can simplify this here too. So we can come to Q is equal to Q final out 1 minus E T CR. This is the equation that we are after. What is the equation? So that is the equation. Right. So this is the equation. So you see, although these equations will look complex, okay, but you can play around them, okay. Just play with them, okay. Try your hands on them, and then you can also get the formulas in mind, and then you work around to see if you can also learn the same thing. I think the point here is you should go back to see mathematics, the differentiation calculus aspect. You grasp how to deal with natural logs, logs, anti-logs, and so on. Then that will make your differentiation very simple. They are very basic and very simple. If you understand that, deriving these equations will also be very easy, right? Now let's look at the work, the energy stored in the capacitor. Let's look at the energy stored in the capacitor. So the energy stored in the capacitor, this is a capacitor. Okay, electrons are coming to make it negative here and make this like positive. So we are charging it. So what's the energy? Okay, now electrical energy, or if you are looking at this electrostatic kind of arrangement. Okay, so the work done is equal to your charge times the potential difference. Okay, so the charge across, the charge moving across this times the potential difference here, potential difference plate, the charge moving across times potential difference. So you see that if you had a graph, let's say you made it charge, and then there's the potential difference. Okay, now this graph comes like that, let's say. So the charges, these are the charges, okay, the unit, this charge. So the charges are being added over, let's say, from potential difference of 0 to potential difference of final. Okay, so these charges are being added up to this point. Okay, so where we are changing Q and changing values for each corresponding. Yeah, when one changes, it gives another value. You can use the graph kind of picture to look at it, and that will make your work very simple. It will make it more intuitive. You'll be able to understand properly. So from here, if we are saying Q is this, and this is V, right? Then you see that we will need to multiply Q by the potential difference. Okay, so Q rises to a maximum. Let's say the maximum Q that we had. Okay, we can assume that move through the potential difference from 0 to this. Okay, so that will be Q times the average. So this is the energy or the work done. Q times the average was potential V. So Q will be times what average potential is V0 plus V final divided by 2. Okay, so we're going to get what Q plus what half. This is the initial voltage is 0. Is going to be half what the V final. So this is work done, the energy stored in the capacitor. Okay, so the energy stored in the capacitor. This is the final charge that we have. Okay, the final charge that we have. Right, so that is that. somebody would also want to say, okay, because if you integrate the charges in the Q, integrate this one. It is from 0 to final. At the end, you come to what? This Q, you say sum this. At the end, you come to Q, final. That's the answer. Times your average. This is going to move from that side to that side, okay? And then from 0 to that, the average will be the answer for V. Of course, if you are integrating, you will need to express, you will need to integrate it with respect to Q. So we must find an expression that will become a little compass. So you can just use this simple calculation. Your maximum, there's the maximum charge that you have, times the average voltage. So the average voltage times the maximum charge that you have, and then that gives you the answer. Somebody can also look at it this way. Why not my maximum VFV, the maximum voltage I have, times my average voltage charge? It comes back to the same. You see it. So you get half Q final. Okay. Sorry, half. So Q final plus Q 0. Okay. So it comes to half Q final times your V final. Okay. So all come back to the same thing. Q final times half V, the same thing. So that the work done is then equal to half Q V. So you can hold 1 as the maximum point, okay, and then multiply through, okay, by the average, right? So I think it's simple to go by this. You can hold your maximum, then the maximum that you have, assume it moved through, the voltage moved through that maximum, okay, that voltage times the average charge. It comes back to the same thing, or the reverse. You come back. So the work done is that. Now you can do substitutions for C. If you want to bring into the equation capacitance, okay? Capacitance is equal to what? Your charge per your voltage. Right. Okay, so that let's say Q is equal to from here Q is equal to CV. So you can put CV here. So that if we can, the equation becomes W is equal to what? Half C V squared. Okay. You can also substitute for V here and put Q there. Okay, so in that case, substituting for V is equal to Q over C. Put Q over C here. Q over C here. What are you going to get? You're going to get what? Half Q squared over C. So just substitution, just play around the equations, okay? So this is the work done for 1. That's the expression for 1. That's it. This is the general equation. The work done is equal to half Q V. That's the parent equation. Okay. Other substitutions can be done. Right. So this is a very good exercise. I think you need to practice more. Okay. As you do that, you become conversant with the equations. Right, now let's look at the connection of electric circuits. So electric circuits, you can have capacitor in series connection, like that. Okay. Then we can have a resistor also in series. Something like this. So here they are in series, okay, that's the same current is passing through. When the same current is passing through, let's say you are in series. Now this will have a certain voltage, was it? Certain voltage. getting voltage. Okay, this will also have voltage, voltage, voltage. Okay, right. So all together they will have 1 voltage. Now, what happens for resistor? The resistors, the sum of the resistors, if they are in series, is R. The overall sum of the resistors, this R1, R2, R3, equal to R1 plus R2 plus R3. But for capacitors, it will be 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. Okay? You can look at the equations like Q over A is equal to C, your A is equal to IR. You can use this to derive the equations. Okay? You can use that one to derive these equations. Now the reverse is true when you have capacitance in parallel connection. As against resistors in parallel connection. Here the voltage is the same. So where the voltage is the same, you can use the same thing. Okay, the voltage across that is the same. Okay, right. So here the resistance, the effective resistance becomes 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And this capacitance rather becomes capacitance, the overall capacitance becomes the sum of the capacitors. Alright, so this is a simple way to let you remember. R straight, okay? The capacitance is, you come down, okay? That is the rule. So the opposite is the same for the two. So this is a relation that you can keep in mind. You can derive it from the principle that I've said. For example, this here, the voltage is the same, of course, okay? Current here, current is different, okay? The voltage is the same. The voltage, of course, of them is the same, but current is different. So that your IR passing through this will give you the same V. So let's say V will equal to your R. R1 is equal to the same I2 in that order. Okay. Now, if you look at it from, let's say, I as the main one coming, I is splitting like that. Okay. Your V will be equal to your I times the sum, the resistance, the effective resistance that will be there. Okay. Right. So you can use that method to derive these equations. Okay. So that V is the same. So V is the same. You look at how the others will also vary. Right. So this is what I mean. So let's assume we have this. So here, okay. Then we know the voltage across this one is the same, but the capacitance of one, this capacitor 2, capacitor 3, we have different capacitors. Of course, the current passing through is different. Alright. Now, when it comes to capacitors, you can use Q to check. Of course, once current is different, the charge going there is different. Okay, so Q is equal to C over. So we have the expression. Capacitance is equal to Q over what? V. So the same as Q is equal to C V. Right, so for each of them, okay, for each of them, Q1 will be equal to C1 being the same voltage. Q2 is equal to C2V. Q3 is equal to C3V. Right? So if you make each of them, this is the same as saying that V is equal to Q1 over C1. Okay, so this will be V is equal to what? Q2 over C2. V is equal to Q3 over C3. And then we are good to go from this side. So from here, from the general equation, you can see that Q is equal to Q1 plus total Q is equal to Q1, Q2 plus Q3. Okay? Or you can also say C1, C total capacitor, okay, will be equal to C1 plus that. So if you are putting this one, Q here, then we're going to have what, in terms of Q, we're going to have what, Q1 is what? C1, V1, C2, V, C3, V. Okay, so this becomes V out, C1 plus C2 plus C3 in this Q, right? Now let this come this way, then you are going to have Q over V is equal to C plus C1 plus C2 plus C3, okay? Now what is this ratio? This ratio is C. So the resultant C is equal to C1 plus C2 plus C3. So this is why in series, in parallel, capacitance is this. The opposite is true for resistance, okay? So you can look at it. You can just sit down and look at the equations and then work around it, okay? But the point is C. In parallel, C is straight. Resistance is reverse for parallel, okay? And then resistance is straight for series, okay? Resistance is straight for series. Okay, so we have series, and then we have parallel, okay? Series, okay? Straight for resistance, so series. Straight for resistance, so it's what R is equal to R1 plus R2, so okay, right. Once you get one, the capacitance is the opposite. That is a simple way to let you remember. So let's look at the Kirchhoff's rules in circuit, okay? So we have this circuit here. Okay. Now, if this is sending out the, let me make this one this way. This is sending current, okay? This will go down. This will go down. And let's assume this is 1. This I2, I3. This is the point, the junction. According to Kirchhoff's, the first, the rule is that I1 is what is giving rise to these two. So I1 will be equal to I2 plus I3. It's the same as we stated that I1 minus I2 minus I3 is equal to 0. Okay, so current entering the point, the junction, is equal to current leaving. Okay, right, that is 1. Now the voltage, so this has a EMF, which is EMF. And then let's say we have a resistor here, another resistor here. Okay, now in terms of voltage, what will happen is this E is what is supplying, assuming we don't have this part of the equation, assuming we don't have this. Okay, now this EMF, electromotive force, okay, that is the force driving the electrons in the cell. We'll cause this one to move. So as it's moving, it will give this one some energy over the potential difference over, and this is also going to get the potential. So this V1, this V2. Okay, it is said that this E will be equal to, because that is the supply of the energies, okay? When the electrons go and come back, the energy used, the energy or the potential across the various loads should be equal to the supply, okay? So it goes around and comes back. So E will be equal to V1 plus V2. That is what it means. Okay, so for a complete circuit, this is a complete circuit. The sum of the EMFs is equal to the sum of the voltages. Sum of the EMFs is equal to the sum of the voltages. Okay, so that's the principle. Once you get these two principles, you can use them. Now, when it comes to currents, when you're talking about currents, you always choose your, let's say you have that. Okay, what you do is this is going, this one, I2, this I1. So the principle can be used here. So this is junction. So this coming in is equal to these two. Okay. Then when you take a complete loop, this is a complete loop. Okay, the sum of the EMFs, okay, should be equal to what? The sum of the voltages. Okay. Right. So you go in that order. You can choose a direction. So this is the direction I've chosen. Okay. Right. So your EMF will be equal to what? This direction. This is in the direction of the current. This is the current going. This bar is opposed to, so the current leaves that part, so it is in that direction. So that EMF becomes positive. Okay, and it goes these ones, it should be equal to these ones. In other words, if you are summing them to become EMF which is positive minus your V minus your V should be equal to 0. Because as it goes, the energy is lost over its surface, lost over that surface area. Okay, right, so that is how to go. In terms of the current, when you choose this direction, because I've chosen this direction, this is in that part, it is in that part, so to be plus, okay, so you have that, okay, and then you have this also then as plus, okay, so for this complete loop, you take a loop, okay, round, okay, so you have that going, natural sense is going to be, if at the junction you have already said this is going down. So if somebody can also choose. So what I want to mean, what I mean is, you choose a particular direction. Let it be so for this. You can choose any direction at all. Okay, but when you choose, maintain the direction. If the current is going against that direction, make the current negative. If it's going in that direction, make it positive. Now, when you work out using this principle and this principle, the answer will, if you get the current to be negative, it tells you the direction that you chose in the diagram is opposite to that one. Okay, so the principle that you should get is at junction, coming in is equal to leaving. In a closed loop, the EMF is equal to the sum of what? Voltages. Okay, that is it. That's the point. Once you get these two, you should be able to solve most of the questions. Then we have the wisdom and range. Now we can blow it out here. Okay, so maybe we have a supplier here. Circuit supplier here. Right, so now what this is, let's say R1, R2, R3, R4. Okay, right, so what will be happening is there will be an adjustment, okay, as we keep on adjusting. Right, so sorry, let's look at our diagram there. Sorry. We have this one. No. This is the point. This is measuring the potential difference here. So that the current doesn't go into this one. Okay. We have this at the diagram. Right. If you look at it from this diagram, let's assume this is a cell. Current is coming, splits here, splits that way, then comes that way, and comes back. Okay, So this is the Wheatstone bridge arrangement. Okay, so this one, you realize that for this and this are in what parallel connection. They are in parallel connection because if you look at this current, the current through this is not the same as that. In series, they will have the same current flowing through them. So here, so far as the current is not the same for these two, we assume that the voltage here will be the same as the voltage here. The voltage across this will be the same as the voltage here. So we said this is what R4 and this R3. So that voltage of R4 is equal to voltage of R3. Now the same principle will work for this one too. The voltage across this one, voltage across 2 will be equal to voltage across 1. So let's rearrange. This is the same as saying the voltage across this one, 4, is the same as voltage is given by IR. Okay? So it's the same as saying what? I R1, sorry, R4, and then this is the current, that's the current with 4 over the voltage here is equal to I3 R3, and this is also going to give us I2 R2 is equal to I1 R1. Okay, now at the balance point, no current flows through this one. Okay, the galvanometer. Okay, so this is at the point where there's balance, no current is flowing through this. Okay, right, so that is it. Then in that case, this I is what comes out here, the same thing I. So in that case, I4 becomes equal to what? I1. Okay, I4 becomes equal to this, becomes the same as what? I1. Okay, and it's the same thing follows. I3 becomes the same as I2. I3 becomes the same as I2. So you see that if we divide this equation here by this and this by that, the i's will be the same. So we can say from here it's the same as saying I. Let me do it that way. This way. Let's turn it. Okay. So we're going to have I4 over. You can divide this. You can turn it. Let me turn it so that we have I2 is equal to I1 R1. Now if you divide this equation 1, this equation 2, divide this equation by this. So you're going to have I4 over I2. So this one. I want 1, and because 1 and 4 are the same, I want them to be on the same side. So let me make it so that they are on the same side, and then that will simplify the equation for me. So this is I1. Okay. And then there's I2. Okay. I'm doing so that because this current I4 becomes the same, or becomes same as I1 here, so that you can have that. So at that point, if you look at this equation, if you divide equation 1 by 2, you're going to get R4 over I1. R1 is equal to I2, and R3 over I2, R2. Now we are saying that I4 is the same as I1, so this will cancel that. I3 is the same as I2, so this will cancel that. So the arrangement comes to from here, the arrangement becomes R4 over R1 is equal to R3 over R2. So let's look at the arrangement. R4 over R1. So you see on the sides, okay? The voltage here, this over this is equal to this over that. So if we know 3 of these ones, we can find the value for 1, okay? And that is one way we can use to find the value for resistor, okay? Right, so that is the point I wanted to prove for the Wheatstone bridge, okay? Right. The potentiometer also works on the same principle at the balance point. Okay, those in parallel, the voltage across those in parallel will be the same. So that one is like you have a resistor along resistor like that. Okay, you are balancing it with another one. Okay. okay, you're shifting it. Okay, so at the point you have no current flowing through. Okay, so the balance point, then this and that are in the same, because there are different kinds of flowing, it's flowing through, then you have the same voltage. Okay, then you can use the same principle A to get your answer. So this is a potentiometer. Right. So we will move on to the next chapter. So let's look at some few symbols. So this is the diode. This is a symbol for the diode. Okay. So we can have the same thing here. Alright. Then we have this coming through. So if you look at the symbol, so we have the light, sorry, this is emitting, okay, so it's emitting, okay, so this is the light emitting diode, okay, this is the diode itself, okay, then you can have the other one, this is a resistor, okay, now of course we have the variable resistor, then we have the symbol in it. The other one I want to talk about is this one. So let's look at this one. Sorry. Right, so we can have this. So this is a thermistor. Then we can have the other one, the same thing. Just a bit instead of having a resistor in here, okay, but this is light dependent, okay. So here is the LDR, light dependent resistance, okay. So these are non-liquid devices, okay. Right. So these ones. So this one, for example, it's light. So this is light, okay. The light falling on it tells how it's going to resist. It's a resistor, type of resistor, but it depends on how light turning on it. Now this is a thermistor, so this rather depends on heat, the temperature, heat, okay. Heat changes its resistance, okay. So this is light.